So this is one of the very key chapters in physics, and in particular for the section of physics called mechanics. In fact, you can say that kinematics and Newton's laws of motion together represent the very basics and fundamentals of mechanics, from which the rest of the concepts are built together. Okay. So one of the aspects of mathematics that you will require to understand the applications of Newton's laws of mechanics is vector algebra, and that is the reason we have just concluded vector algebra before doing this, because particularly things like vector addition and component algebra of vectors is going to be very important in terms of applications in this particular chapter. So anyway, that doesn't matter for us because we have just done vectors. Okay, so all that is fresh for us in our memory, and I don't think there should be any difficulty with the application of vectors in this chapter. So anyhow, let's start by understanding the statements of Newton's laws themselves. Okay, so as you know that there are three laws given by Newton. Okay, the first one is called the law of inertia, because it defines a property possessed by any body or any mass or any particle called inertia. So the property of inertia is such that so any body in a state of rest, okay, or motion, whichever be the case, has a tendency to continue in the state of rest and say continue in its state, whatever be that state, whether it is a state of rest or state of uniform motion. Or uniform motion. So what does uniform motion term mean over here? Motion with uniform velocity. Okay. Until and unless an external force acts upon it. This is the property of inertia. This is the property that is called inertia. So this is the statement of Newton's second law. Now, of course, you'll also understand here that the inertia of a body or for that matter even a particle is measured in terms of its mass. Okay. Larger the mass, the more inertia the body has. The greater the inertia. And mass, as you know, is a fundamental property of all matter. So whether we are talking about a very, very small particle like a neutrino or a Higgs boson or even an electron or something, or we are talking about an everyday, macroscopic object like a cricket ball or something even very huge like a building or an aeroplane or whatever, everything possesses the property of mass and thereby possesses the property which we call inertia. So all bodies possess the property of inertia, and by this property what happens, a body wants to continue in its state, whether that state is a state of rest or it's a state of uniform motion, and to change its state, that is if it's at rest to bring it to motion, or if it's already in motion to change its uniform motion into an accelerated motion or decelerated motion, or make the velocity vector turn or whatever be the case, to basically change its motion from uniform motion to non-uniform motion. That means make its velocity vector change. We need to apply some external cause on it. Something external has to act on it. Until that happens, it's not going to change its state. And that external thing that acts on it, causing it to change its state of inertia, is called force. So the statement is that until and unless an external force acts upon it, the body will have a tendency to continue in its given state. Yeah, Sakshi, the chapter is there in the heading in Newton's laws of motion. As I told you in the last lecture also, we are starting with this new chapter, Newton's laws of motion. Okay. So I think all of you should have the module of this by now, whether you got the physical copy of the module or you just got the PDF, but it has been distributed to you. Yeah, module 2 has 2 chapters, basically Newton's laws of motion and friction. So we'll start with Newton's laws of motion. Other than that, we will also be following a reference book in this, the concepts of physics by H.C. Verma, that particular reference book. So at the end of the lecture, I will explain that to you. Okay. So anyway, so hope all of you are clear with the statement of first law. Okay, so let us understand this in a little bit more detail. So for example, if we have this situation that on a frictionless horizontal surface, or on a very smooth horizontal surface, like a polished marble surface, or even an ice skating rink surface which is made of ice, so very little friction involved. So we have some kind of a block. Okay. At rest on a smooth surface. Okay. So we know that this block will continue to be at rest. That can happen forever also, unless what happens, unless an external force acts on it. If you don't apply any external force on it, it will not change its state of rest. It will remain forever in the state of rest. Okay. So that is the property of inertia. In fact, this is the inertia of rest. The inertia property of a body at rest. So that we can call as the inertia of rest. Okay. And the larger the mass of the body, or in this case the block, the more it will have a tendency to oppose this change, or oppose the external cause which might cause it to start moving. The more the tendency to remain at rest, the larger the mass of the body. Okay, so hence we say that the inertia is measured by the mass of the body. Okay, so just write down the statement, Hitanshu. It's like self-explanatory. There's nothing more in it. It's like, now another example of the property of inertia would be something like this, that instead of the body being at rest, if we have a situation where we have a body which is moving along a smooth surface, it's already in a state of motion. Okay, so if the mass of the body is m and is moving at an initial velocity u, okay, so this is a block of mass m moving on a smooth horizontal surface at velocity u. So it possesses a certain physical property which we call momentum. Okay. So it has what we call momentum. We use a symbol momentum, p for momentum, and it is nothing but mass into velocity. So momentum for a body is defined as mass multiplied by velocity. But it's a vector quantity, remember. So it's the momentum vector. Okay. Now we know that if we want to stop the body, for example, okay, then we have to apply some retarding force. On its own, it will not stop because it's on a smooth surface. Now, in order to slow down the body, okay, eventually make it stop, okay, or even accelerate the body, that is, make it speed up. Okay. External force must be applied. Okay. Until and unless we apply the external force, okay, its momentum P is equal to mass into the initial velocity tends to remain constant. Okay. So in the above diagram, if we are not applying any force, we'll see that if this was the situation at time t equal to 0, after some time also, the body continues to move at the same momentum, because there's no external force acting on it. Whereas if we want a situation where the body should be slowing down, if we want this thing to happen, that initially it had a momentum of m into u, because it's moving with this velocity u at t equal to 0. But after some time, we want that, by the time it's t equal to t, we want that the body is slowed down, its momentum has reduced. So now its momentum has become some p prime, where the magnitude of the velocity is less than the initial velocity. So for this to happen, we know that we have to apply some external force, and we have to apply the external force in this way. We have to apply it in such a way that it opposes, keep applying this force, so that this kind of a force will tend to give it this kind of an acceleration. Okay. So to decelerate the body or slow down, okay, force must act on it. Okay. Or even if we want to, instead of make it decelerate, alternately, suppose we have a situation where we want to make the body accelerate, even then we have to apply some kind of force. On its own, it will not accelerate. In the absence of force, the body will tend to continue in its state of uniform motion. So we want this, that initially our momentum was mu, okay, but I want that after some time the velocity is increased in magnitude, so the body is undergoing what we call accelerated motion. So now this vector has a longer this thing, okay, the velocity vector. So the new momentum mv at some time t, we want that magnitude of v should be greater than magnitude of u. So we want to accelerate. So that will only happen, as you know, if we apply some accelerating force. We have to apply force in such a direction that it produces acceleration instead of producing deceleration. So you'll have to apply a force in this way on the body. Until and unless some kind of force like this acts on it, we will not get the required acceleration. Okay. So to accelerate the body, okay, so speed it up. We want to increase its speed. The body, so to accelerate the body, okay, again force must be applied. In the absence of force, what will happen? In the absence of any force, the situation which we have shown in the first diagram will happen. When there's no external force, its momentum remains constant, or it has a tendency to continue in a state of uniform motion. So this property, this is collectively called the inertia of motion. These examples are showing us the property of inertia of motion. That is, a body in motion tends to continue moving uniformly. If we want to change that uniform motion into either accelerated motion or decelerated motion, we have to apply some kind of external force. So this is the second type of inertia, which is called the inertia of motion. The first type of inertia we saw above was called the inertia of rest. So just make a note of this. Okay, Ayush, you want to go through the example of inertia of rest once more? Okay. So see, after defining Newton's first law, which all of you know actually, is something very well known to you from class 9. So we've defined inertia in general. Okay, this is the property of inertia. So we started with one example showing the inertia of rest. So that is very simple. If you have a body which is at rest, it will continue indefinitely at rest. To make it move, we have to apply some kind of external force. So this property is called the inertia of rest. Whereas the second example we are showing, that is the inertia of motion. Okay, so just take your time to write this down quickly. No, yes, I think it is not an issue of language. Okay, this is things that you are supposed to know from class 9th and 10th. So if you're having too much difficulty with this, then you can go through your NCRT class 9th also once. Just understand the background of Newton's laws of motion from that. Or if you're from state board, then go through your SSC textbook from class 9th. Okay. There is nothing difficult in what I've explained over here. In fact, if you just write down these examples line by line, you will be able to understand. Okay, so there is nothing complicated about Newton's first law. It's a very simple definition that every body has a property of inertia. So what is the property of inertia? It is the tendency to continue in its state, whether the state is the state of rest or the state is the state of uniform motion. Now, any body just wants to continue in that state until and unless some external force acts on it. So this tendency is called inertia, and Newton's first law just defines that property of inertia. You still haven't written the first example? Okay. Write it down fast, please, people. Okay, Rupesh, doesn't matter. Just write down the statement, okay? When we discuss about second law and the numerical applications, you will understand how momentum changes with force. Momentum देखो क्या है, mass into velocity है ना. So अगर momentum को change करना है, that means velocity has to change. So when will velocity change? When there is acceleration. If the acceleration of a body is zero, like in the first example I've shown above in this place, no force is acting, so there is no acceleration. So what about velocity? It will remain constant. So if velocity is constant, what about momentum? It's constant. Because you just see momentum is defined as mass into velocity. Momentum vector is defined as mass, which is a scalar, multiplied by velocity vector. So if acceleration of a body is zero, then by kinematics you know that velocity is uniform. So if velocity is uniform, it implies that momentum remains constant. Simple. Got it now? But अगर मैं body पे force लगा रहा हूँ, like either I'm applying the force opposite to the momentum or in the same direction as the momentum. So if I'm applying opposite, this force will tend to decelerate the body. So now see acceleration vector, how it's pointing. It's pointing opposite to velocity vector. So it will cause the velocity to decrease in magnitude. It will cause a deceleration. Whereas if I apply the force in the same direction, it will cause an acceleration. We tend to accelerate the body. But either way, what is happening now? The momentum is changing. If the acceleration of the body is not zero, that means velocity becomes variable. Variable का मतलब क्या? It changes. So therefore, what about the momentum? That's also variable now. It's changing with time. So that is what the law of inertia is saying. That if you want to change the momentum of a body or change its state of motion from uniform motion to non-uniform motion, we have to apply force on it. It will have a tendency to continue in uniform motion until and unless what happens, external force acts on it. Okay. So hope all of you finished writing down these two examples. Now let us continue forward to Newton's second law, and this is one which is the most important law for us here because it will explain it is the part which we will use in the numerical applications. Newton's second law. The first law is just a simple definition. It tells you about property of inertia. कि ऐसा हर बॉडी के पास एक प्रॉपर्टी होता है which is called inertia. It can be a very small particle like an electron. It can be a very very large body like a entire planet also. It can be an entire planet. It can be a bus or whatever. Anything which has mass has the property of inertia. Now the second one basically tells us the relationship between momentum and force. So that is the one which is important for us. Okay. So let's come to Newton's second law. Okay, this is one of the most famous laws in physics. Everybody has seen this law. Even students of arts and commerce, if you ask them what is Newton's second law, everybody can shake their heads and say, yeah, we know what is Newton's second law. So let's understand. So Newton's second law statement, However, there's a misconception. A lot of people say that Newton's second law is F is equal to ma, force is equal to mass into acceleration. In fact, let me tell you that is wrong. That is not the proper statement of Newton's second law. Okay, F is equal to ma, but that is a conditional statement, and we will understand कि वो क्या condition में true होता है. But वो generic statement नहीं होता है. F is not equal to ma in general. Okay, in general, the second law is defined in this way, which I'm writing now. The net external force acting on a body equals to the rate of change of its momentum. Okay. This is the proper definition of Newton's second law. Okay. And it's more or less in the same language that Newton had given it in the 1800s. Okay. If you read the original text of Newton's classical mechanics textbook also, you see it's more or less the same statement. So this can be written by a simple equation that the net force acting on a body equals to rate of change of its momentum. So this is where our application of calculus also becomes important. Rate of change का क्या मतलब है? So यहाँ पे in this statement, this which I've written on the left hand side, F net, this is the net external force acting on a body. Okay. So by that we mean it is the vector sum of all forces acting on it. Okay. So for example, if we have some kind of a body of mass m, okay, and on this body a number of external forces are acting. We have, can be any odd shape, so I'm just taking an arbitrary shape. Now on this body there are a number of forces acting, f1, f2, f3, whatever, like this. There are some n number of forces acting. So there are forces f1, f2, f3, like this, going up to some n number, act on a body. Okay, then we will define the net external force as basically what? As the vector sum of all the forces acting on it. So it will be F1 vector addition with F2, vector addition with F3, up till the last force. Okay. Even if n is a very large number like 500, so we'll have to add 500 forces in that case to find out what is the net force. So this is what we mean by the left hand side. Okay. And on the right hand side, and P is momentum of the body. So P is defined as mass into velocity, which we've seen before. Okay. So dp by dt is nothing but rate of change. What we know in calculus now, rate of change of momentum with respect to time t. Okay, rate of change of momentum with respect to time. Like in calculus, you know that dy by dx, it is the rate of change, instantaneous rate of change or differentiation, okay, of y with respect to x. So it's that same operator that we're using, a rate of change operator. So these are the two sides of the equation. Okay, net force is equal to dp by dt, or rate of change of momentum with respect to time. So make a note of this first, and this is the important law for us. From now on in this chapter, mostly we will be concerned with solving this equation. Vector sum of all forces to find out the left hand side, which is the net force, and that should equal to the rate of change of momentum. Now you might be thinking what happened to mass into acceleration, because you are used to writing net force is mass into acceleration. So that will also come. We will understand it in the next step. But as I told you that F is equal to ma is not a general statement. It is a conditional statement. It applies only in certain conditions. Whereas this statement that we have written over here, which is the original correct form of Newton's second law. It is a general statement. In any and every situation, it will be applied correctly. That the net external force acting on the body should equal to the rate of change of its momentum with respect to time. Okay, now let us further understand about rate of change of momentum. Now this next part is very important. The right hand side of the equation, the RS is rate of change of momentum. This thing. Okay. Now in this we know that momentum is mass into velocity. So next step we can write it as rate of change of mass into velocity. Now for a rigid body, for example, a block, okay, a solid sphere or cylinder or plank or rod or any such thing, for a rigid body, the mass is constant. The mass m, it is constant. It's not changing with time. Okay. So therefore, rate of change of momentum dp by dt, which is this, can be simply written as mass into rate of change of velocity. This is the property of differentiation that you know. Okay. So this becomes this, but only in this condition that we are talking about a rigid body. So rigid body का मतलब क्या है? That उसका mass constant है. So when the mass is constant, then we can make this conditional statement that rate of change of momentum becomes this. And further, this condition reduces, we know that rate of change of velocity is defined as acceleration. This is a kinematics definition जो आपने पढ़ा है. This is rate of change of velocity with respect to time. So that is defined as acceleration. So then what happens? which is equal to this, now becomes mass into acceleration. Okay. But this last part, that rate of change of momentum is mass into acceleration, is provided mass m is constant. Okay. Mass should not be variable. Okay. Now you might ask that अच्छा ऐसा कौन सा situation है जहाँ पे mass variable है? Okay, generally any body we talk about its mass is constant. So I'll say that yes, generally speaking any body we talk about, because we are talking about rigid bodies, it's true that mass is constant, but there are many situations where the mass of a body is not constant, and in that case it is not a rigid body, it's a different type of body, and we'll discuss about that also. So this statement that we generally tend to think that net force is mass into acceleration is all right, but remember it is all right provided this condition is satisfied, that the mass is constant. If the mass is variable, then this statement will not be correct. F net will not be mass into acceleration. So just make a note of this part now. This is very important. Okay. So from here you can see that this becomes mass into acceleration. So rate of change of momentum can be equated with mass into acceleration provided the condition that mass is constant is held true. One very simple example I tell you, that if you have an ice block which is continuously melting, so as it's melting, it's losing mass, no? Because the water is going out of the block. The ice cube is losing its mass. The total mass of water plus ice will remain constant, but the water is not part of the block anymore. As some part of the ice melts, it loses contact with the block. Okay. So an ice block which is in a process of melting is an example of variable mass body. So it's not a rigid body, it's a non-rigid body because its mass is changing with respect to time. Its shape is changing with respect to time, its size is changing. Whereas likewise if we have a solid metallic block or a solid wooden block or something like that, which is not undergoing any kind of state change or shape change, then it's what we define as rigid body. उसका मतलब क्या है कि its mass is constant. So yes, that is true that most of the time when we apply Newton's laws, we are talking about rigid bodies. So F is equal to ma will be correct for us. But remember the exception case, that if mass is variable, then we cannot say F is equal to ma. We have to use a different type of mathematics there. So of course the question does arise that if mass is variable, then how will we represent the right hand side of the equation? So that also I'll give you a brief explanation of that. But in this chapter, we will not be dealing with the applications of that kind of thing. Okay, variable mass will come in a different chapter, which we'll be studying 2 or 3 months from now, which is called center of mass or system of particles. for a body of variable mass. So for example, an ice block at room temperature. So this is melting at room temperature. So what happens? Its mass, it is decreasing with time. Okay. Or another example could be, you have a tanker which has a leakage. So you have a tanker and it contains some kind of liquid inside, but the level of liquid is decreasing because it has a leakage. So what happens again? The mass is decreasing with time. Okay. Or you have an example of an industrial conveyor belt. You must have all seen some kind of examples of conveyor belts in industrial processes. It is like a belt which is being moved with some velocity because of the action of the rollers underneath it. Now, typically, onto the belt, there is some mechanism by which mass is being dropped. Okay. So there is, so let's say we have a industrial conveyor belt, and concrete is being dropped onto it. So what is happening? Its mass is increasing with time. So these are all physical examples, everyday examples of situations where the mass is variable. So for such a body, what happens? Rate of change of momentum, this cannot be equated to, this is not equal to mass into acceleration. What it's equal to, we'll discuss about. Okay, but first of all, we have to understand that rate of change of momentum is not equal to mass into acceleration. So these are the exceptions where we cannot say net force. We cannot say net force is equal to mass into acceleration. This is not true when mass is variable. And these are the examples, some of the examples of variable mass systems. So for a proper technical understanding of Newton's second law, you must know that this exception exists. Rate of change of momentum equal to net force. We cannot always say it is mass into acceleration. There is that special case where it is not the situation, and that special case is nothing but where the mass is variable. Okay, so hope you've written this down. So briefly, I'll explain how Newton's second law works in a variable mass situation. But as I said, this is not required in this chapter. So when mass is variable, rate of change of momentum, which is differentiation of mass into velocity, this becomes rate of change of mass or into velocity plus mass into rate of change of velocity. This is by product rule in differentiation. So this becomes velocity into rate of change of mass plus mass into rate of change of velocity, or it becomes instantaneous velocity into rate of change of mass plus mass into acceleration. So this is the situation for variable mass systems. But this will not be required in this chapter. So this is not needed in Newton's law of motion chapter. We will be studying this in more detail. It will be used in the chapter system of particles later. It is just a general sort of precursor. I mean. In Newton's laws of motion chapter, we'll always deal with rigid bodies. So mass is constant. So you can see this is basically a special case of this equation. If mass is constant, then this term dm by dt is zero. Okay, so just make a note of this. Okay, so hope you have written this down. So this is clear. So for Newton's second law applied to rigid bodies, we'll simply use this equation that net force is equal to mass into acceleration, because mass is constant. Okay, so for the moment you need to only worry about this. Okay, so let's look at some examples next. So we come back to a situation of a smooth horizontal surface, and we have initially at rest, we have a block of mass 10 kilograms initially at rest. Now from t equal to 0 time onwards, we start applying a horizontal external force. So from t equal to 0 onwards, a constant horizontal force F is applied on the block. Okay. As a result of this, the block has a displacement of, let us say, 4 meters after 2 seconds. Okay. So first of all, find the acceleration A in meters per second square, and find the magnitude of force F in newtons. Very simple question. Just the application of this basic equation that we've written on top. Just try this out, people. Okay, so the block is initially at rest. No, there you have to do the calculation again. It's simple kinematics. Use your regular kinematics equations. Try again. Yeah, anybody else got the answer? Correct. Lusker, your answer is correct. So देखो, the first thing you have to understand here that the net force F is constant. How we know it's constant? Because it's given to us that it's a constant horizontal force. So that tells me that the acceleration A, that A will be F by m. Okay, that is also constant, because if F is constant, so we have uniformly accelerated motion with u equal to 0 at t equal to 0. Okay, some acceleration which we don't know, but the displacement is how much? It is 4 meters at t is equal to 2 seconds. So which equation will you use? We'll use this equation that when acceleration is uniform or constant, we have the three standard equations. V is equal to u plus at, S is equal to ut plus half at square, V square is equal to u square plus 2as. We just have to make use of the second one. So you can see that 4 meters should be equal to half into some unknown acceleration into 2 seconds ka square. So you can see that the acceleration is 2 meters per second square. So that's the first step. Now we know the acceleration. Now we go back to Newton's second law. So this was the first part. On the second part, Newton's second law, on applying it by using this relation that net force is equal to mass into acceleration. Here that net force is that single force F. So we have this. So F is equal to the mass which was given to us as 10 kgs multiplied with the acceleration which we just calculated, 2 meters per second square. So the force we are applying is of magnitude 20 newtons. Okay. Because you also know that the SI or standard international unit of force is Newton, okay, or N, where 1 Newton equals to 1 kilogram meters per second square. This is the, whereas CGS unit of force is dyne, where 1 dyne equals to 1 gram centimeter per second square, or 1 dyne equals to 10 to the power minus 5 newtons. This is also something you should know. How the displacement is 4 IUs, that is given in the question. Read the question again. अंडरस्टूड ना. क्वेश्चन में वो दिया हुआ था कि इट इज ऑब्जर्व दैट उसका डिस्प्लेसमेंट 4 meters है आफ्टर 2 seconds. So on that basis we had to calculate what is the force. If that information was not given, then of course we cannot calculate. So this is part of the information given in the question. If this was not given, then we cannot calculate. Okay, so pretty simple as you can see. Okay, so make sure that you remember this system of units also. The SI unit, the standard international unit, is Newton, where we define 1 Newton as 1 kilogram meter per second square. Whereas the CGS system of units, the centimeter gram second system of units, in that the force unit is dyne. So 1 dyne is 1 gram centimeter per second square. So as you know, 1 gram is 10 raised power minus 3 meters. Okay. 1 centimeter is kg. 1 gram is 10 raised power minus 3 kg, or 1,000th of a kg. 1 centimeter is 1/100th of a meter. Okay, so that's how this becomes 10 raised power minus 5. So this conversion also you should remember. Okay. Generally, we will be solving questions in SI system only, but in case you have a question where the data is in CGS, you should know how to convert. Okay, let's look at our next example. So similar kind of situation. Smooth horizontal surface. The block is of mass 5 kilograms, but this time we are applying two forces on it. Okay. So the block is initially at rest, and we start applying two forces. One is F1, it is of magnitude 12 newtons. We also start applying a force from the opposite direction, like this. This is of magnitude 7 newtons. Okay. So initially the block is at rest. Okay. So initially the block is at rest when two forces at opposite directions start acting on it from t equal to 0 onwards. Assume the forces are constant. So find acceleration of the block in meters per second square, the velocity of the block at 2 seconds, the displacement of the block after 5 seconds. So this is very similar type of question as the previous one, but instead of one force, there are two forces acting on it. So you'll just have to use the concept that the net external force, it is the vector sum of all forces. So in this particular case, we will have to write the net force as the vector sum of the two forces F1 and F2 that we are applying. And then next step, we will apply the Newton's second law, that this is the case because obviously mass is constant. So combination of these two equations you will have to use. Yes, Ruxar, very good, that's correct. And once you found the acceleration, it's very easy to find the other two things because you have to just use the kinematics equations. So in this case, because the two forces are acting in opposite direction, correct, Uday, that's good, that's correct. So because the two forces are acting in opposite direction, what is happening is that the vector sum f1 plus f2 will in fact have a magnitude of 12 minus 7 because the angle is 180. So you just apply your basics of vector algebra. When we talk about okay, good, that's correct. Okay, so first step, you need to find the net force, okay, which is the magnitude of f1 plus f2. So वो यहाँ पे कितना हो जाएगा? That will become 12 minus 7 because f1 and f2 are at theta equal to 180 degrees with respect to each other. So the net force will have a magnitude of 5 newtons. Okay. And net force will be mass into acceleration. So the acceleration will have a magnitude of 5 by 5 or 1 meter per second square. Okay. So as this block is moving like this, we have an acceleration of 1 meter per second square because that will be the direction of the net force. F1 will dominate. So F1 का magnitude ज़्यादा है compared to F2. So the direction of the motion will be along F1, but the net force will have a magnitude of F1 minus F2. So once you got the acceleration, rest of the things are very easy. For velocity, you can use at because u was 0. Now, if you want to write this as a vector quantity, you can write it as plus I cap in meters per second square, taking this direction as your x-axis. So 1 into 2, 2 meters per second, or velocity as a vector will be 2 I cap in meters per second at t equal to 2 seconds. And similarly, the displacement, just use the equation half at square, because again initial velocity is 0. So s will be equal to half into 1 into 5 square. So the displacement will be 12.5, again along the positive x-axis in meters at t equal to 5 seconds. Okay. So if we're just talking about magnitudes of the three quantities, they'll be like this. Whereas if you are expressing them in vector form, you can express them like this. So this is clear. This is very simple stuff. So that is the basic aspect about Newton's second law. Now we will see many types of applications of Newton's second law. Almost this entire chapter is about numerical applications of Newton's second law. But before that, let us also conclude our study of the three laws by understanding the third law. This is the one which also everybody knows. Okay. And not only everybody knows, but most people who know about Newton's third law have done some kind of experiment to verify it also. Okay. So I'm sure all of you have experimented the action reaction principle by know impacting a force on somebody's face or on somebody's person. You just verify that okay, if you apply a action on them, is there equal opposite reaction or not? It's a very simple way of inflicting force on somebody in the name of science. Good opportunity. Okay. So this is called the action reaction principle. That every action has an equal and opposite reaction. So at a very basic experimental level, if you slap somebody very hard, they experience the slap and they experience the pain of the slap, but your hand also experiences an equal and opposite pain because your hand experiences the equal and opposite reaction force. Okay. So this is the painful truth about Newton's second law. If you inflict a serious punch on the wall, you can break your hand because your hand will experience an equal and opposite amount of reaction force. So you can damage your wrist or break your hand or something if you try to apply too much force using your hand on a rigid object like the wall or something. So these are painful truths of Newton's second law, but Newton's third law. But actually, it goes much deeper. Okay, and we'll discuss about that. So what this basically means that if a body, let's say A, applies a force which we'll call the action, okay, on another body B, and this force will denote by FBA. That is, we're using the system of index that this is the force on B, okay, applied by A. So we're using B comma A. So then, according to Newton's second law, it implies that it implies that the body B will apply, it will definitely apply an equal and opposite force, which we typically call the reaction on A. And that force we can now denote with the symbol F A comma B. So this symbol is now the force on A applied by B. This was the force on B applied by A. Okay. So now Newton's third law basically states that these two forces are equal and opposite. So the force applied by B on A will be equal and opposite to the force applied by A on B. So the reaction is equal in magnitude and opposite in direction to the action. And every action has a reaction which follows the principle. So this you can see that the magnitude of this reaction force is equal to the magnitude of the action force. And direction of FAB is opposite to force on B by A. So this is a more sort of technical way of expressing Newton's second law. That if a body A is applying some force on B, then by definition B must apply an equal and opposite force on A. This is just a universal truth of about all types of forces. Okay, so let's understand this in context of some physical examples. Yeah, uh, these laws can be applied to a single body, a system of bodies, anything in general groups. That's correct. So, for example, if we have, let's say, an electron and a proton, okay, kept at a certain distance. Now, what will happen is that the force that the electron experiences because of the proton will be equal and opposite to the force that the proton experiences because of the electron. This is the force on the electron applied by the proton. This is the force on the proton applied by the electron. So an electron and proton apply equal and opposite force of attraction on each other. Okay. So the force on the electron by the proton is equal and opposite to the force on the proton applied by the electron. So this is a fundamental truth about the nature of electrostatic force. This is an example that basically shows you the nature of electrostatic force. This is given by something called Coulomb's law, which we'll study later in 12th. This is part of class 12 portion. But you can understand this aspect of Coulomb's law, that the attraction force applied by one particle on the other will be equal and opposite to the attraction force on the other particle because of the first. And that aspect is nothing but Newton's third law. So it's a universal law. It applies to two fundamental particles of nature. It applies to two rigid bodies. It applies to two gigantic planets or a planet and a star applying gravitational attraction on each other. It applies to everything. Okay. Another example, a situation where we observe action reaction principle. Imagine this is the top view of the carom board, okay, and this is the striker. Top view, and this is a coin. Now this is stationary initially, and we have set off the striker with a velocity like this. Let's say we are even, we are actually not aimed the velocity vector towards the center of the coin. So it's going to make one of those tangent shots kind of things. Okay? So after some time, so when the striker comes in contact with the coin, the situation will be something like this. And the striker would have moved along this kind of line, so it would have, say, come somewhere here, because we had set it on a path like this from its initial position, which might have been here. So it came, and now during the impact or collision of the two, what will happen is that we will observe that the coin experiences a force like this, and the striker experiences equal and opposite force like this. So this is the force acting on the coin applied by the striker, and this is the force the equal and opposite reaction force applied by the coin on the striker. So as the striker hits the stationary coin, it applies an impact force, which we can think of the as the action on the coin. But the coin will apply an equal and opposite reaction force on the striker. So this pair of forces also has this property that the force applied by the coin on the striker is equal and opposite to the force applied by the striker on the coin. So this is an example of action reaction during a collision. Right, so this is clear. So this is about action reaction principle, Newton's third law. Now we will come back to applications of Newton's second law. That is net force is equal to mass into acceleration, or mass being constant. Now, one type of example we'll see is equilibrium condition. That is when a body has zero acceleration, even though multiple forces are acting on it. Okay. So basically, what is happening is that the acceleration of the body is zero, even though we might have various different forces acting on it. So in this case, acceleration equal to zero implies that net force is equal to zero. So that implies that the sum of all the forces, this vector sum, whatever n number of forces are acting, that must be zero. So the equilibrium condition is this, that the net force on the body is zero. So this statement is called the equilibrium condition. The net external force acting on a body is zero. So this is an important application of Newton's second law. That what happens when the body is having zero acceleration, but there are forces acting on it. It means the forces are acting in such a way that their vector sum or the net force acting on the body is zero. नहीं बेटा मास क्यों जीरो होगा उसका एक्सीलरेशन जीरो है ना मास तो इनर्शिया प्रॉपर्टी है that is independent of force and everything else. Remember, mass is not affected by inertia. I mean, mass is not affected by force. Mass is inertia. It's the fundamental property of the body. But because acceleration is zero, no? So mass into acceleration is zero. Understood the point? So the most basic example of this is suppose a person is so a person of mass, let us say 50 kilograms, is vertically suspended, okay, and at rest by the action of a vertical force F, which is acting on his hands in the upward direction. Okay. So given that acceleration due to gravity is 9.8 meters per second square. Find the magnitude of the force. Okay. So this is the most basic example of something. Imagine a person is hanging like this, but he is kept from vertical free fall by some kind of force which is acting upwards on him. Okay. So maybe he's in this kind of situation where his hand is being held by another person who's over here. So this person is holding him like this. So the person is applying some kind of vertical force, okay, on this person. So let's say this person A, this is person B. So A is held vertically by force F applied to his hand by the person B, like this kind of situation. So it's very simple. We have to understand that for the person on his body, there are two forces acting. One is gravitational force mg, which will be 50 kg into 9.8 meters per second square. So that will be 490 newtons. Okay. But his acceleration is zero. So this force now has to be balanced by some other force. This you want to find out. So acceleration is zero. That means net force has to be zero. So that means F minus mg, because F is acting the opposite direction to mg. This has to be zero. That means the amount of force that has to be applied vertically on him equals to his weight, but is in the opposite direction. So it has to be 490 newtons. Okay. So very simple example. Hope this is clear to you. Okay, so hope this example is clear. So let's look at one last example now. Now this same person, now there is some force acting on both his hands from either side. Okay, so there is one force F1 and one force F2, which are both acting in such a way that they are at 30 degrees to the horizontal, and the mass of the person is 50 kgs. So if two symmetrical forces F1 and F2 act as shown to keep the person of mass 50 kg at rest in a vertical plane. Okay. So again, G is acting like this. So basically, the person is hanging by the action of F1 and F2. Okay. Find their magnitudes. Very simple question. Just work this out, people. So realize that in all, on the person, there are three forces which are acting: gravitational force, F1 and F2. Okay. And their vector sum should be 0. F1 plus F2 plus mg, they should be 0 because the net force is 0 because it's in equilibrium. Okay. So now you know these angles are 30 degrees. So you have two options. One is what we just learned in the last lecture. You can use Lami's theorem. In Lami's theorem, you can see that the three vectors whose sum is 0. Okay. Now they are such that you can see this angle is equal to 30 plus 90, 120 degrees. This angle is also same, and this angle is also same. Okay. So vector sum of these three is 0, means that f1 upon sine 120 is equal to f2 upon sine 120 is equal to mg upon sine 120. So here we don't even have to solve anything else. Sine 120 is common to all of them. So magnitude of both these forces are equal and they are equal to the weight. So that is equal to 490 newtons. In this case, because the forces are applied symmetrically at 30 degrees to the horizontal. If the angle was something else, then the force would have been something else. Okay, all depends on the values given. But for this particular question, as you can see, this becomes a solution. Okay. So hope you understood this equilibrium condition, and with this we end today's class, people. So make sure you note down this example, and I will be sending you the notes and the recording. So do the revision of this before next week. Whereas the remainder of this week, since you have the test coming up on Sunday, make sure you do a revision of vectors And tomorrow's lecture also we'll be doing some revision question in vectors. Okay. So that's it for today, people. Wish you all the best.